In the last video, in part 1, that is, in our introduction to convolution, we began with this formula that if you're multiplying or not multiplying, taking the convolution of two functions, they have to be the function of the same variable, in this case t, what that amounts to is taking an integral where now they are not functions of t, but they become functions of x inside of the integral sign. So this is a function of x. The function that's on the right-hand side of the star becomes a function of t minus x dx. So inside the variable, or inside the integral, the variable is not t, it is x. Here the t is just treated as a constant, integrating with respect to dx, and these are the limits. And if we write our functions down in the opposite order, like this, again, we apply the same set of rules. This would be not g of t, but inside of the integral, g of x, and for the function that's on the right-hand side of the star, inside of the integral, it's not f of x, but f of t minus x, where now the variable is x, t is just treated as if it's a constant. And in part 1, we were kind of demonstrating the concept of convolution with a specific example, and we wanted to demonstrate is that this does equal this, even though we're writing them down as two different integral expressions. In fact, these two integrals are equal to each other, and we were demonstrating that with a specific example. And in part 1, that is in the previous video here, these were the two convolutions, switch their order. Here's how they were written in integral form for each one. We evaluated this integral. It gave us the expression t over 4 minus 1/8 the sine of 2t. Now we're going to evaluate this integral, which corresponds to this expression, and see if it gives us the same answer. So that's what we're going to do right now. So we're going to erase this and now work with this integral to see if it gives us the same expression as this one. That is t over 4 minus 1/8 times the sine of 2t. So 1/2 the integral sine of 2x, let's put parentheses around so we don't confuse anything, times t minus x dx. Let's make this bigger. X goes from 0 to t. So this would be t times the sine of 2x, but t is treated like a constant, so it can go to the outside. So this will equal t over 2, the integral of the sine of 2x minus 1/2 x times the sine of 2x. And again, x goes from 0 to x equals t. So let's look at this one here. Here we have t over 2 times the sine of 2x. The integral of the sine is minus the cosine. That would be minus 1/2 the cosine of 2x times 2. So this one, the first one, just gives us minus t over 4 times the cosine of 2x. And x goes from 0 to t. And now here we have x times the sine of 2x. Again, that's all set up to integrate by parts. When we do that, we get this expression, minus 1/2 times 1/4 the sine of 2x minus x over 2 times the cosine of 2x. And again, x goes from 0 to t. And this is just integrating this integral, again, by parts, what we remember from elementary calculus. So let's go ahead then and make our substitutions. Here we have, this will give us minus t over 4 times the cosine of 2x. Okay, and we have where x equals t, so that will be the cosine of 2t minus x equals 0, that's the cosine of 0, or that is 1. So we have that, and then here we have another cosine term in here, where we have cosine of 2 times t, and then we will also have 0. Well, let's go ahead and take it like this, minus 1/8 times x equals t, that's the sine of 2t, minus, when x equals 0, that's the sine of 0, so that's just 0. Then multiplying here we have plus 1/4 and then we have x cosine of 2x, x equals t, that's the cos t times the cosine of 2t. Again, that's plus 1/4. X equals t, cosine of 2t, t, with the 1/4 here, minus x equals 0, that's 0. So we have minus t cosine of 2t plus, those two terms cancel. This is plus t over 4 minus 1/8 the sine of 2t. So this integral right here for the final answer gives us this, and in fact, as you just saw a few minutes ago, this is also the solution to this integral, which we worked out in detail in part 1 of our video. So these two in fact are equal. So we didn't prove it, but what we did was we gave a demonstration that f of t, taking the convolution of the function f of t and g of t, is the same, gives the same answer as taking the convolution of g of t with f of t, even though we have two different integral expressions. And again, the way we obtain the integral expressions is just kind of blindly following this procedure that f of x inside of the integral we write it, f of t inside the integral we write as a function of x. For the function on the right hand side of the star, it's a function of g of t minus x inside of the integral dx. Here, g of t inside the integral becomes g of x. Here on the right hand side of the star, not f of t minus x dx, and the same limits in each case. So this integral expression is equal to this integral expression. And we haven't proven that actually, but we did demonstrate it with our specific example here, where here we're taking the convolution of a function just t, 1/2 the sine of 2t. Now we reverse the order. When we write down this in integral form, here's f of t is just t. Inside the integral it's f of x, that's just x. This is g of t to the right of the side of the star. Inside of the integral is g of t minus x. This is sine of 2t minus x dx. When we reverse the order here and write it in integral form, now this is f of t. Inside of the integral it's f of x. We just have 1/2 sine of 2x. This is our g of t. Inside of the integral, g of t is just t. Inside of the integral is just t minus x, corresponding to g of t minus x. And what we've demonstrated then is that each of these integrals has, for its final answer, was t over 4 minus 1/8 the sine of 2t. And notice that these integrals do give us a function of t. In this case here it's t over 4 minus 1/8 times the sine of 2t. And again, the reason why convolution is important, as we will prove in a future video, is that if we have our functions f of t and g of t with corresponding Laplace transforms, if we take their convolution to get another function, some function of t, take the Laplace transform of that, the Laplace transform that we get is the same thing as multiplying f of s times g of s. And again, we will prove this in a future video. But this is why convolution is important in the study of differential equations, the way it relates to Laplace transforms. Or if we take the inverse Laplace transform of each side of this equation, we'll have the inverse Laplace transform by multiplying two Laplace transforms together. Take the inverse. The answer that you get is the convolution of their respective functions, f of t, g of t. In other words, here we have f of t, here we have a function g of t. This corresponds to a Laplace transform of f of s. This corresponds to a Laplace transform of g of s. If we multiply these together, and then take the inverse Laplace transform, that does not equal f of t times g of t. It equals the convolution of f of t, g of t. And we will prove this in a future video, but this is why the concept of convolution is important in our study of differential equations. And of course, in the earlier videos in our series, we dealt with Laplace transforms quite extensively. Okay, that'll be it then for this video. A reminder that the playlist for all the videos is at the website digital-university.org.